Okay, everyone, let us get started. So, welcome to this bootcamp called as Hands-on Reinforcement Learning. Let me start sharing my screen. Okay, so firstly about me, I'll be the instructor for this course. I'm one of the co-founders of Visuara. I have pursued my BTech and MTech from IIT Madras, and after that, I have pursued my PhD from Purdue University. And then after completing my PhD, all of us, me, Raj and Sridath, we returned back to India and we started this venture with a mission to make artificial intelligence really accessible for all. And we are covering a topic today called reinforcement learning, which has always been somewhat in the sidelines up until this year, where DeepSeek was released and suddenly reinforcement learning came back into the limelight again. So let's get started. First of all, why did we start this bootcamp right now? Uh, so one of the main reason was the release of this paper called DeepSeek R1. This paper came out uh, in the January of this year, and it really shook the world. And the reason that happened was that before DeepSeek came, in the September of 2024, OpenAI had released their first reasoning model called OpenAI O1. But the problem was that this was a complete black box. People had no idea how they had made reasoning work. It could be anything inside the black box. And when DeepSeek R1 came out, it had accuracy levels which were quite comparable to that of OpenAI O1, which made people suddenly realize that, okay, whatever these people have done in the paper, it must be similar to the recipe which O1 has followed. And I want to take you to one figure in this paper called, this is a this is a figure which is called as the aha moment. Just take a look at the caption of this figure. It says that an interesting aha moment of the intermediate version of DeepSeek R10. The model learns to rethink using an anthropomorphic tone, and this allows us to witness the power and the beauty of reinforcement learning. So DeepSeek showed that you cannot induce reasoning in an LLM without having reinforcement learning at the heart of it all. And after DeepSeek paper was released, there has been literally a spurge of reasoning models coming out of all the AI labs. Everyone, Gemini, Anthropic, OpenAI are continuously releasing reasoning models. Recently, there was a model called Kimi K 1.5, and this entire paper is dedicated to reinforcement learning. So reinforcement learning has suddenly caught the limelight, and people have started to take it very seriously. Another reason which I personally feel why RL is going to be very important in the coming years is because if you look at where we are right now, where we are presently, we are using a lot of LLMs, right? But these LLMs have a very important phase called pre-training, which is trained on a huge amount of data. So we are still operating in the era of human data. Without the knowledge of the data, the LLM is not really smart. Now we are slowly entering into the era of experience. What does the era of experience mean? It means that the agent will experience events by itself, learn from those experiences, and iteratively improve from those experiences. So we don't have to give a lot of data to the agent, but the agent will acquire the data by uh, interacting with the environment and learning from it. And this is exactly what the field of reinforcement learning actually talks about. So, so far, right, reinforcement learning had been associated with these video games. A lot of you might have heard that RL is used to play Atari games, and that was a big breakthrough moment. And then AlphaGo was another example where reinforcement learning was used to make artificial intelligence really clever in these games, but no one really applied RL to LLMs in the last 2, 3 years. In fact, ChatGPT could not have been made without the invention of reinforcement learning through human feedback, which was at the heart of aligning the LLMs towards human preferences. So, the reason I'm talking about all of this is because I really think from the bottom of my heart that reinforcement learning is going to be a very significant driver in the AI revolution in the coming years. And we should focus to understand the concepts behind RL and then slowly, progressively understand how reinforcement learning is used in large language models. Now, how has RL progressed through the years? If you look at the timeline, the field itself is not very new. It has been around since 1950s, and from 1950 to 1990 is the era which we call as classical reinforcement learning. And then after 90s onwards, we had a transition towards policy gradient methods. And 2013 onwards, people started talking about using neural networks in reinforcement learning problems. So the field of deep reinforcement learning was born. And then 2018 onwards, we started using RL in LLMs. So you can see there are these four eras which the AI community has seen with respect to reinforcement learning. So whatever we are going to cover as a part of this series, you are going to be closely witnessing the work of brilliant scientists through multiple decades, how they have invented these algorithms. And we could not be here using ChatGPT without understanding the contributions of all these giants from 1950s. So this course is going to be arranged in such a way that we cannot truly understand modern reinforcement learning unless we appreciate classical RL, because classical RL is really at the heart of it. And then we are going to slowly advance and move towards modern reinforcement learning and understand how reinforcement learning is used in large language models. That is going to be one of the key focus in this bootcamp. So, what is my goal? My goal is three things. First thing, to help you deeply understand the theory behind RL, to give you the confidence to set up and write codes to solve RL projects. Recently, I was having conversation in our company, and people have this general belief that reinforcement learning is a very theoretical field. They don't really know how to build RL agents on their own. So my aim is to break that perception and give you a sense of how reinforcement learning can be practically deployed. It is as simple as deploying neural networks using PyTorch or TensorFlow. So I want to help you get that confidence as well. It's not going to be just a theoretical course, but it's going to be very practical also. That's why the name is very suggestive. It says hands-on reinforcement learning. And then I want to help all of you develop a deep sense of enjoyment for the field. I have a specific bias towards reinforcement learning compared to other disciplines within AI, because I believe that RL is something very close to the human experience, whereas other fields are not that close. But as you will see in this lecture, reinforcement learning is quite similar to how humans think. So you will feel a natural sense of understanding as I'm progressing through the topics. And then when you see an agent actually learn from experience, it almost feels like I'm simulating intelligence in my computer. So I had that feeling when I first implemented these agents on my own. So I want to transfer that deep sense of enjoyment to all of you as well. And then my teaching style is that I'll not be assuming any prior knowledge. And I believe that an easy lecture is always better than a lecture in which people say it was hard to understand. So that is my philosophy, and I'm going to be focusing on the fundamentals. One thing I've realized is that if your fundamentals in RL are very clear and very spot on, it helps while you're using reinforcement learning algorithms in practice. So you need to have an understanding of the theory as well. So now let's rewind 50 or 70 years back and try to be in the shoes of all the people who were discovering this nascent field at that time. First of all, let's understand what is the reinforcement learning problem. So the reinforcement learning problem, we'll understand this by first considering the other two types of ML problems, which are called as supervised learning and unsupervised learning. So supervised learning is a type of a problem where you are given a labeled data set. For example, let's say I'm given a labeled data of MRI scans of benign tumors and malignant tumors, and I train my AI model to analyze this data. And whenever a new MRI scan comes, I make a prediction that this MRI scan belongs to the benign category or the malignant category. This is a classic example of supervised learning. Why is this called supervised learning? Is because we have we have been given data that is labeled. Here the labels are malignant and benign. So the broader objective of a supervised learning problem is to learn from the training data set and generalize or extrapolate to situations which are not really present in the training data set. And it heavily relies on data set which is labeled. Without labelings, you cannot use the supervised learning method. This is the first type of AI model. The second type or the second classification is called as unsupervised learning. Unsupervised learning is quite different from supervised learning because here we do not have any labels. Imagine that you are hired as a group of scientists and you visit a garden and you are given the task that here is a scale, go ahead and measure the length and width of the petals and sepals of all these flowers and tell me how many classes of flowers are there. So this is a problem where you do not know how many species of flowers are there in the garden, but you collect all the data and you try to classify the data into different clusters. Now remember that we are not given any labels here beforehand, but we are just looking at the data that we have collected and we are trying to group the data into clusters. So clustering is a method which is often used to solve unsupervised learning types of problems. The objective here is to find structures which are hidden in collections of unlabeled data. Now let's come to reinforcement learning and let's see how it compares to both these categories. So supervised learning has data which is labeled. Unsupervised learning has data, but that data is not labeled. In reinforcement learning, the model is not fed any data at the start, but the model acquires data through interaction. So this is one of the crucial difference between supervised, unsupervised, and reinforcement learning. The reason it acquires data through interaction is that oftentimes in reinforcement learning problems, it is impossible to provide all the set of input-output pairs of data because that will be a huge data set. Imagine you are playing a game of chess and you are trying to develop an reinforcement learning agent to play your chess moves so that at the end you win the chess game. How much data can you give in the game of chess? There are 10 raised to 44 possible configurations of the chess pieces on the board. It's impossible to provide that much data set. So the best option is to help the model learn from interaction. And by the way, this is very similar to how humans learn. Just think back to the time where you learned to bicycle for the first time. Someone taught you, you made a lot of mistakes, and then you slowly, iteratively improved. This is exactly what happens when we use reinforcement learning. Then the objective of supervised learning is to generalize to situations not present in the training data. Unsupervised learning, we find hidden structures in collections of unlabeled data. But in reinforcement learning, the objective is to maximize a goal or a reward signal. This is one of the fundamental differences between reinforcement learning and other types of ML algorithms. Here we try to maximize a reward signal. Now, this is something you will not encounter in the other algorithms. So we can summarize this as reinforcement learning problems involve learning what to do, how to map situations to actions so that we maximize the reward signal. In fact, many of the core RL algorithms were actually inspired from biological learning systems because it's quite similar to how humans think about situations, really. Um, Now, if you're a scientist working back in the 60s or 70s, people will not take you seriously because people had a notion that all these methods which talked about learning from experience are weak methods. They did not really believe in them because any task which involved a lot of planning was considered to be very complicated, and they did not think uh, machine learning can be used to solve such a task. So that's why this field did not make a very rapid progress because it was always hindered by these thoughts coming from scientists which uh, said that don't focus too much attention on these problems. It's not leading anywhere. Instead, try using other algorithms like maybe genetic algorithm was quite popular at that time. So let's think of some real life examples of reinforcement learning to understand this better. Uh, the first example is a master chess player trying to make a move. Now, this is a move which is not based on data which is acquired in the past, but it is based on what will happen if I play this move. What are the next 10 moves which my opponent is likely to make? And which move right now makes the most sense? You need to have intuitive judgments about the desirability of all these moves. So, immediately when you look at this problem, you see that you can't bucket this in any of the other types of ML problems that we talked about. This has a different level of complexity because we are not given labeled data. In fact, we are not given any data. We are collecting data as we are generating more and more experiences. The second example of a reinforcement learning problem is that let's say we take an example of a gazelle. Imagine an animal which is just born, a calf who is trying to learn. Now, people have noted that this gazelle calf, after 2 to 3 minutes of birth, it's struggling to get up. But then it's learning from interacting with the environment. It's making a lot of mistakes. It's adjusting its movement patterns. And then half an hour later, it is seen running at 36 kilometers per hour, which is really amazing. So this is one example. Another example is imagine that we have a mobile robot. Imagine a vacuum cleaner, which automatically goes ahead, moves inside the room, and then collects trash and puts it in the trash can. Now, when you are designing such a robot, there are multiple questions which this mobile robot has to make. One of the question is that should I go to a new room in search of trash, or should I go back to the charging station? These are actions which the robot has to take. Now, these actions have to be based on some things, and those things which I'm talking about are the current battery charge of the robot and how much time in the past it has taken to find the recharger in the past. And then the final exam is relatable to all of us. It's us preparing breakfast or eating something. Whenever we are preparing our breakfast, we perform a series of actions very fast. We walk to the cupboard, open the cupboard, select the cereal box. We reach for the cereal box, grasp it, retrieve the box. Then we obtain a plate, spoon, sit down, and eat. So there are a series of actions taken. In fact, in all these four examples, you can see there are a series of actions taken, and all of these actions have been directed towards a common goal. We are going to come to the common goal after some time, but try to think before I move ahead, what will be the goal in all these four cases? Remember, I said that in reinforcement learning, one of the major differences from other algorithms is that there is a goal which the agent has to achieve. So, what would the goal be in all these four scenarios? In some cases, the goal is quite straightforward, but in some cases, you might require to think a little bit. Okay, so now what is common in all these examples? In all these examples, we have a very active decision-making agent, and then that decision-making agent is interacting with the environment, in order to maximize a certain goal. Now, what is the goal in all these cases? In the first example, when we are playing the chess game, the goal is obviously to win the game, right? In the second example, when the calf learned to run very fast, the goal was to run fast. The goal for the mobile robot is maximum trash collection, and the goal while preparing our breakfast is to obtain highest nourishment. So these are the goals of the reinforcement learning problems. And then there is a decision-making agent. So in the first case, the agent was the chess player. In the second case, the agent was the gazelle, then the mobile robot, and finally, agent was Phil. And in all these cases, there was an environment which the agent interacts with. This environment varies from problem to problem. In the first case, the environment was the chessboard. In the second case, the environment was nature. In the third case, the environment was the room plus battery. And in the fourth case, the environment was kitchen. You can see I have marked a star over here because there is a slight intricacy here. Sometimes the environment is actually inside the agent also. Like if I'm deciding what to have for breakfast or how to prepare my breakfast, the environment is not just the kitchen, but also the memories in my mind also constitute the environment. But that's a little bit complex, so let's not think about that. I would request people not to mark anything on the board here because it stays here now as I move ahead. Okay, so now in all these examples, the agent is using its experience to improve its performance over time by interacting with the environment which surrounds the agent. So this is what is common, and in fact, you will see me using these words, I think more than 500 times in this bootcamp: agents. Then you will see me talking about environment. You will see me talking about goal. So I want you to really internalize these terminologies, because whenever we are going to look at any problem, let's say LLMs or video games, we are going to first ask the question, what is our agent here? What is our environment here? And what is our goal here? So these three pillars are probably one of the most important concepts you need to understand in the field of reinforcement learning. Now we are going to look at the elements which constitute a reinforcement learning system. So there are four elements of a reinforcement learning system. The first element is called as the policy. The policy is what defines the agent's way of behaving at a given time. So let's take the example of chess. Okay, so imagine my opponent has made some move and I want to make a next move. So this will be decided by your policy. Your policy will basically look at the current configuration of the chess pieces and tell you what is the best possible action from that state. So in a very formal way, policy is a mapping from states to actions. So for example, let's say there is a state S1 and you have four possible actions: A1, A2, A3 and A4. So policy tells you that among these actions, which is the best action for you to perform. So maybe it's A1, A2, A3 or A4. So policy is something which tells you how to behave in a certain situation. Then the second is the reward signal. The reward signal basically defines the goal in a reinforcement learning problem. Again, let's think back to the analogy of chess. When we are playing the chess game, the reward doesn't come momentarily from one step to another step, but the reward comes directly at the end of the game. So the reward is maybe +1 for winning the game. The reward is -1 for losing the game. And if the game is a draw, then the reward is 0. So one of the, I would say, complexities in reinforcement learning is that in several cases, like the chess game, we receive rewards which are delayed, which are received towards the end. Immediately, I don't receive my rewards. So that's the meaning of a reward signal. It is quite similar to the pleasure or pain that you feel in a biological system, right? If let's say there is a pan of water and uh, I'm boiling water in that pan, and if I touch that pan, immediately body gives a reaction that okay, this is very hot. And the first time when that happened to you, uh, you got a reward signal that whenever I touch a hot vessel, it causes a lot of pain. And that reward signal was important because without that reward signal, you would never know that you are not supposed to touch hot vessels because it causes a lot of pain. That's why reward signals are important. When you are learning how to ride a bicycle, your parents might have told you, don't do this. If you do this, you will fall down. And in some cases, you would have actually fallen down. So that's a reward coming from the environment which says that don't do this, otherwise, it will cause pain or it will make you fall down. Then we come to one of the most important concepts, which is called as the value function. A very interesting incident happened in our company recently. I was giving a presentation talking about how reinforcement learning is used in playing video games, and a lot of people, they were beginners in reinforcement learning, and the entire discussion came down to a very intuitive understanding of value function. So I want to try my best to explain the meaning of value function here so that when we come to such problems, you'll realize that an intuitive understanding of this is at the heart of us understanding those problems as well. So reward signal indicate what is good in an immediate sense, right? There is an immediate signal when you touch that hot boiling vessel. But value function specifies something which is good in the long run. So let's take an example to understand this. Okay, so let's imagine that we are the coach of uh, a tournament, and let's say we have to pick 11 players for every match in the tournament, and there are 14 matches which are going to be played in the tournament. Now let's say you pick a player X. Okay, so we'll call it this player as XP. This is the name of the player. And in the first match, this person plays very poorly. So I'll say poor. So this is a reward, right? This is an immediate reward that this person has played a very poor match. Now, will you take an immediate decision of removing this player after the first match? Probably not. If you are a wise coach, you will not look at immediate rewards, but you will see what is the value this player is bringing to the table and how much is this player going to perform, not in the current matches, but in all the matches combined. So finally, the performance of this player is going to be dependent on this is the first one, second, and all the 14 matches. So your decision is not just going to be dependent on R1, which is the immediate reward, but your decision is going to be dependent on R1 plus R2 plus dot 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 R14, which is the addition of all the rewards in the future which you are likely to get from this particular player. This is exactly the meaning of value of that player. Or in the reinforcement learning context, we call it as value of a state. Uh, and this is the main difference between rewards and values. Rewards are something which look at short-term desirability, whereas value is something which focuses on long-term desirability. Whenever you are playing a move in chess, you don't look at, okay, if you look at immediate rewards, if I take the queen of an opponent, is that going to win you the game? Probably not, because you need to think long term. Even if I don't take the queen of the opponent right now, maybe this move will help me after 10 moves played by my opponent. So this is where we are prioritizing the value of that move as opposed to the reward received from that move. This is one of the crucial differences between the reward and the value. And I would say this was one of the most significant contribution of these researchers from 1960 to 1990. Just the ability to put into words what humans do quite naturally is, I think, remarkable. And they mathematically tried to express it using a function called as value function. So, and then still people did not really understand the value of reinforcement learning at that time, because remember, we are still talking about 60s, 70s, 80s, where the field was just being born. But these terminologies have stayed same over the years. People have not really changed it. And the fourth one is called as the model of the environment. So the model is something which mimics the behavior of the environment. If you are giving a certain input, the model will tell you what the output will be. Now, typically, most of the environments model will not be given to us in this boot camp, because that is something which replicates most of the practical scenarios. Uh, there are some very simple scenarios where you know the models, but if you are, let's say, trying to learn a bicycle, right? You won't exactly know that if I put my pedal in a certain way, what's going to be the ground reaction, what's going to be the orientation of my cycle. If you can boil the entire physics down to some model, then great, then you can model the environment. But in most of the practical cases, it doesn't make sense to model the environment, because we'll anyways end up making a lot of approximations. So there are two types of RL problems. There are model-based and model-free methods which are used in most of the reinforcement learning cases. And we'll be looking at model-free methods in this bootcamp, because they are representative of most of the practical problems which we are going to encounter in this bootcamp. Now, what we'll do is we'll look at one practical example, which is the game of tic-tac-toe. And we will use the four elements of reinforcement learning to understand the general idea of using reinforcement learning to solve this game. Okay. So all of you are aware of the tic-tac-toe game. We do crosses and the opponent does O's. And then we have to make sure that all the crosses are either in a vertical, horizontal, or in a diagonal line. So now what we are going to do is we are going to uh, build an algorithm which can play the tic-tac-toe game against an opponent. Okay, so let's try to think step by step. So our goal is to construct a player which can find flaws in the opponent's play and maximize the chances of winning. So what is the state here? So remember that the state is the observations which you are receiving from the environment. And then based on those observations, you are trying to take some actions. So the state is whatever the current configuration of the tic-tac-toe game is. That's the state in this case. So let's say this is the current configuration. Okay. So this is what the state means. The state is the current configuration of the tic-tac-toe game. And the policy is what is going to tell me that if for every given state, what is my best action in this state? For example, here, probably my best action is this, right? Because I want to avoid the diagonal O's being formed. Otherwise, the opponent will win the game. So my policy will tell me that which location I should place the cross on based on the state I am in. Okay, and then one of the most important constructs in this game, in this algorithm, is going to be the value function. So the value function which we are going to define for this game is, for every state, we assign a number which gives the latest estimate of the probability of winning from that state, and we draw up a table. I'll explain what I mean by this. So if this is the state, then the value is 1 because you can see that I have already won the game. So the value is the maximum of this state. Similarly, if this is the state, my opponent has won already. So my probability of winning now is 0. So the value is 0 in this case. For all the other states, I will assign an initial value of 0.5. Now, obviously, you know this is wrong because let's construct a particular. So let's say if the state is something like this. Uh, like this. Now, this one has a very high value, right? Because I'm just going to do this and win the game after this state. But right now, I do not have any knowledge of the environment. I do not have any model of the environment. So I'm going to give a random assignment of 0.5 to all of the other states. And my objective is going to be to play the game so many times that I adjust the values of all these states to reflect the probability of winning from that state. Okay. So this is what I'm going to do. I'm going to construct an initial table, which will be a very bad table. It will be a very bad approximation. But I know it's a bad approximation. I want to get better and better. I want to learn from experience. So how am I going to learn from experience? Let's look at one move. Okay. Let's say we are here. This is the state. And we want to play our next move. Okay. So what we do is we look up the value function table and we see that there are 1, 2, 3, maybe 7 to 8 options where I can play. How many options are there? 7 options are there. Okay. There are 7 possible states I can play as my next state. But where should I place the cross? Should it be here, 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 here? What will I do? So what I'll do is, let's say the value function table is like this. It assigns a value of 0.5 to this state, 0.6, 0.55, and 0.4. So it's natural that I will choose the state which has the maximum value. Okay, I'll choose this state as my next state. This is called as exploitation. We are selecting the state with the greatest value. And I keep doing this. But then there is one small caveat here. Instead of selecting the best value always, what I do is I sometimes take a random guess, maybe 1 out of 10 times. So if these are all my possible next states, I'll deliberately select one state randomly as my next state. Even though I know that it is not the most optimal state to select because its value is 0.4 and clearly there is another state with a value of 0.6, but I will make that move nonetheless because I want to explore all the possible states on the board. So this is called as exploration versus exploitation. Exploitation is where you always make a move which is the optimal move. But sometimes when you do that, you might end up not seeing the other states ever. So that's why you end up making a move which is completely random. Now, okay, this is fine, but you might ask the question that this is okay, Rajat, but didn't you set the initial values of as 0.5? So how are these values changing? If we are anyway selecting the best value, wouldn't they stay 0.5 as always? When are we changing the values? That is what I am coming to next. While we are playing, we actually change the value of the states we find ourselves in based on the value of the next state. So what we do is we adjust the current value of the state to be closer to the value of the next state that we play. For example, let's say this is the state, okay? And this value is 0.5, right? And then after this, I play this move, but this value is 1. So the advantage of this should go back to this state. Basically, we should tell our algorithm that we are reaching this state only because this was the previous state. So we increase this number by some small amount delta, which is towards the value of this state, next state. And generally this delta is some factor into the difference of these two, that is 0.5. So this is how we do it. We change the value of one state and move it closer to the value of next state. And the reason why we do that is because at the end, if I win or lose, I want all those changes to be back propagated along my earlier sets of moves. And this is what will allow me to do it. Now, this is something which is at the heart of majority of the reinforcement learning problems that we'll look at in the future. I do not expect you to understand this alpha formulation right now. We will cover this separately in a lecture. All I want to you to understand is how we are designing our algorithm to make the best use of the value function, because the value function is at the heart of this whole process. Remember, initially we set the value functions as 0.5 to all these states, but as we play more number of games and we backtrack the values of the states and make them closer to the values of next states, we slowly start to see these tables changing their values. Because let's say there is one particular move which leads to a loss of the game. So that value will be decreased from 0.5 to maybe 0.3. Similarly, if one move is leading to a winning of a game, that value will be increased from 0.5 to maybe 0.8. That's how these tables will change their values from the initial set of values. Okay, so now there is a simple diagram which helps you understand this. I will share this in the notes. I want all of you to go through this. Okay, so till now what we have seen is that there are 4 elements of a reinforcement learning system. We have the policy, which is telling us how to behave. Here the policy was simply the policy said something like this: I'm going to look at the value function table, and for every state, I'm going to pick the best value, but with a small probability epsilon, I will choose a random value. So maybe for 10 times, I'll choose the best value, but out of 10 times, I'll end up choosing a random value. So that is my policy in this case. What is the reward? Here the reward is actually something which we are not seeing here that much, because we are just focused on the values. So what are the values here? The values are the probability of winning from that state. That is what is the value of this particular state. We are going to look at a very formal meaning of value, but essentially value means the summation of all the rewards which the agent receives from one state till the end of the episode. Okay, so this is how we are defining the value. In this case, we define in terms of probability of winning from that state. And then last option is model. What is the model? Here we do not assume any model. So uh, this is a model free case. Okay, so these are the 4 elements of a reinforcement learning system that we looked at. And another thing we looked at was that the main feature which distinguishes reinforcement learning from supervised and unsupervised learning is, firstly, we are not given a lot of data. As in this case, you see, there is no data given to us, but the model simply learns from experience. And secondly, we are always moving towards a goal. Here our goal was winning. We want to win the tic-tac-toe game as much as possible. So we are always constantly striving to win. Everything that we do, everything our policy does is only for that one objective of winning the game. Now, what we are going to look at is we are going to reinforce our understanding of these concepts by looking at a very formal way of defining this whole problem. Uh, so I'm going to revise all of this through this second part. And this is where we are going to focus on this topic, which is called as finite Markov decision processes. Okay, so first let's understand something called as agent environment interface. Whenever we are going to look at any reinforcement learning problem, I am always going to ask you the question, what is the agent environment interface here? Agent environment interface is something like this. You have an agent. The agent is receiving some observations from the environment. So I'm denoting observations by OBS. And based on the observations, the agent is taking some actions. Okay. So, and based on these actions, the agent is interacting with the environment. So this is the environment and the agent is receiving a reward. It's not just receiving a reward, but it's receiving a next observation also. Reward plus next observation. And this is how you connect both these loops. So it's also formally expressed like this. So this is the diagram which I was showing. The agent receives a state from the environment, which is called as ST. This is also called as an observation. And then based on the observation, the agent performs an action. And then this action is fed to the environment and we get the next state, which is the next observation and the next reward. Then again, this next state is passed to the agent and again an action is taken and this loop continues. In most of the cases, this is one of the most important steps in understanding reinforcement learning problem. I want you to start thinking at the back of your mind, if we are applying RL to LLMs, what would the agent environment interface look like? And I really struggled with this because it's not very apparent. Who is the agent? What's the environment? What's the state? What's the action? What's the reward? So it's not always that straightforward for most of the cases, but we are going to develop a better understanding of the agent environment interface as we go along. Okay, so again, four things. First is the state. The state is the information or the observation the agent receives from the environment. Based on this state, the agent performs an action. This is denoted by A of t. And then one time step later, the agent receives a new reward and goes into a new state. So the reward is denoted by RT plus 1 and the new state is denoted by ST plus 1. As I'm going along, I'm also going to focus on some mathematics so that you develop an understanding of the theory from not just a verbal point of view, but from a mathematical lens also. And then you might ask the question that for each state, I said that the agent performs an action, but how does it know which action to perform? This is where the policy comes in. The policy is something which defines a mapping from the states to the actions. For every state, the policy tells you what is the probability of selecting each possible action. And then you end up choosing an action based on the policy. For the tic-tac-toe game, we had a policy which is called as an epsilon greedy policy. What does that mean? First, let's look at the greedy policy. Greedy policy is where we select the best action for all the states, always. But epsilon greedy policy means that for a small probability epsilon, maybe 1 out of 10 times, I will choose a random action. So that is the meaning of policy and it's always denoted by pi. I have been always curious where this pi notation comes from, but it's been followed continuously in all the literatures. Right from 70s, 80s to the modern papers on LLMs, we always see the symbol pi being used for policy. So we are going to stick with that notation in this lecture also. Okay, let's move ahead. So we are going to look at some practical examples of agent environment interface and see whether we are able to construct this interface. Okay. So let's look at a bioreactor. In the bioreactor, what's happening is that there are a bunch of sensors. Then there are some heating elements and there are some motors inside the bioreactor. And the objective is to produce some chemical which is useful. So what are the states here? The states are simply the observations. What are the sensors detecting? Well, they are detecting the readings, the temperature readings, maybe the moisture readings, the thermocouple readings. So whatever information you see or get from the environment and is stored in the sensors, that is the states. What are the actions? Based on this information, you are going to decide what's the target temperature for your heating element. What's the target stirring rate for your motors? That's where the action is going to be performed. And the reward is the moment to moment measures of uh, the rate at which the useful chemical is produced. So typically these states and actions are written in the format of a vector. So you club multiple states into single vectors. So to summarize, the states are sensor reading, thermocouple reading. The actions are target temperature, target stirring rate, and the reward is the rate at which useful chemical is produced. And then you can simply draw this diagram to get some more confidence like, okay, what is our agent? It's the bioreactor. What's our interface? You can just call the environment as environment for now. Then what are the states here? These are the states. What are the actions? Then you feed the actions to the environment, you get rewards. What are the rewards? These are the rewards. So an exercise for all of you would be to convert these discussions into diagrams like these. The second example is a pick and place robot. These robots are usually employed in conveyor belt settings or industries, factories where a lot of manual tasks are automated. So here the states are the readings of the joint angle and the velocities. So here you can see how many joints are there. We have one joint here, we have one joint here, and then we have one joint here. So probably there are three joints. So at every joint, I can read the angle of the joint, which is this angle, and how fast is the angle moving, which is the velocity of that angle. Okay, and then based on my observations, my actions are how fast are my motors going to move? How fast is this gripper going to rotate? How fast is this arm going to rotate? How fast is this arm going to rotate? All those are actions. But after the states and observations are defined, what are my rewards? Here the rewards are very simple. The reward is +1 for every object that is successfully picked up and placed, and the reward is -0.02 for a motion which is very jerky. So usually the rewards are very simple to define, and it should be like that. If you complicate a reward too much, then you'll end up in trouble. For example, if you are playing the chess game, the reward should be simply +1, -1, and 0 for winning the game, losing the game, and draw the game. If you assign some reward like 0.5 for taking the queen of the opponent, this will mislead your agent to think that maybe I should prioritize taking the queen over winning the game, but this is not really what you want, right? And this brings me, or this reminds me of the famous incident which happened in the AlphaGo game, where the AlphaGo AI agent made a very random move, which is called, I think, move number 37. And no one in the Go community had even thought of making that move, and everyone thought that AI had gone crazy, but it ended up winning the game after that. So that was pretty amazing, actually. You can go up and read on that move. It's a very famous move. Okay, so here the states are the angles, angular velocities. Actions are the voltages which are applied to the motors. And the reward is +1 for successfully object picked and -0.02 for jerky motion. Sometimes when you think of the rewards from scratch, you might feel a little bit lost. It used to happen to me before, but as you see more and more problems, the reward becomes very clear to you. And if you immediately think of a reward, it probably means that you are going in the right direction. You should not overthink the reward that much. Now we are going to look at the rewards again. So again, an example of chess, as I mentioned, rewards are +1 for winning, -1 for losing, and 0 for drawing the game. Uh, if you are constructing a agent environment interface for a maze and you want to move the robot to escape the maze, the reward is -1 for every time step that passes before the robot escapes the maze. This, I think, is a very intelligent reward because if the robot escapes the maze in 100 time steps, the reward is -100. But if the robot manages to escape the maze in 5 time steps, then the reward is -5, which is good, right? So it's reinforcing or promoting actions which allow the robot to escape the move as fast as possible, and it's penalizing actions which are making the robot stay in the maze for a longer time, which is exactly what you want. So this is a very nice reward. Then robot collecting empty soda cans, it's straightforward, +1 for each can collected, otherwise the reward is 0. Okay, so now we are going to look at one important concept which is called as returns. I have interacted with a lot of students who have learned reinforcement learning, and many of them still don't understand the difference between rewards and returns, which I find very interesting. Like if you have actually studied the subject, this is one of the most important differences, but you need to understand it properly. Now, the goal of a reinforcement learning agent is not to maximize the rewards. It is to maximize the addition of all the rewards which the agent receives from start of the episode to the end of the episode. And we have a separate word for the addition of all those rewards, which is called as a return. So the agent's goal is to maximize the cumulative reward it receives in the long run, and it's called as expected return. The reason it's called as expected is because there is some amount of randomness or stochasticity in all the models which we will encounter with. So if you are in a given state and from that state you reach the end of the episode, let's say you make 100 moves. For every move, you can get different returns, and expected return basically calculates the average of all those returns. So basically, the expected return is the cumulative reward which the agent receives in the long run from the start of the episode to the end of the episode. And it's denoted by this symbol G of T. This is also the community in RL is incredibly consistent with respect to notations. In all the papers, you will see this notation consistently being followed. And it's written as something like this: RT plus 1 plus RT plus 2 plus dot 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 RT. What this means is that if I'm at time step fifth and someone asks me, Rajat, what is the reward or what's the return for time step fifth? So what I will do is I will first complete the entire episode from that time step to the end of the episode, and I'll calculate R6 plus R7 plus R8 plus, let's say, R50 is the time step when my episode ends. And this is what we call as T here, which is the final time step in our notation. So that's the basic difference between immediate rewards and expected returns. Our goal in reinforcement learning is not to maximize immediate rewards, but to maximize the expected returns that we receive in the long run. Okay, now this formulation, or you might have heard me saying the words episodes a lot of times. Why am I using these words? Uh, it's because most of the applications of RL that we are going to see they have a final step. That is, the episode ends sometimes. Like when you are playing the game of chess, the game ends at a certain time. When you are solving a puzzle or you are going through a maze, the puzzle or the maze ends at a certain time. There are some tasks which do not end, which keep on going continuously. Imagine that you have sent a rover to Mars or Moon, and the task of this rover is to navigate the surface of the Moon or the Martian environment to collect a lot of data. Now, this is not an episodic task because it's not going to end, it's going to continue forever. So, this formulation is not correct, right? Because there will not be a final step in when you are sending a rover to the Martian environment. So the interaction with the environment will continue forever. So these are called as continuous tasks. So there is a difference between episodic tasks and continuous tasks. Most of the examples that we are going to see are going to be episodic tasks. Imagine playing video games. The game ends at a certain time. Let's say you have 3 lives. After you lose all your lives, the game ends. Continuous tasks are somewhat rare, but we do see them in certain cases. Now we will understand a very important concept in reinforcement learning, which is called as discounting. And we'll understand this concept with the help of an analogy. Let's imagine a 100 rupee note. The 100 rupee note is more valuable right now compared to 5 years later. This is because for the same 100 rupee note, if you get 20 biscuits right now, you probably will get uh, how many? Maybe less biscuits in the future. So the value of those notes will actually decrease in the future. This is because of the inflation. And the concept of decreasing value with time is also applicable in reinforcement learning problems. So rewards that are received immediately are considered to be more valuable compared to rewards that are received much later in time. And we take this into account by saying that every reward is gamma times less valuable than the reward which has been received before. So let's say the first reward I receive is called R1, the second reward is R2, and the third reward is R3. If we apply discounting here, we will change this to R1 plus gamma times R2 plus gamma times R3 plus gamma square here. And you can see we are reducing the value of these rewards because gamma is, let's say, 0.5, gamma square is going to be 0.25. So we are essentially giving more weightage to immediate rewards, and we are not giving a lot of weightage to rewards which are received too long into the future. And this is something which uh, is actually used. This discounting factor is used in most of the reinforcement learning problems. Uh, yeah, and we are going to understand this with the help of an example in some time. But let's look at a mathematic formulation for now. Remember, g of t was the expected return. And initially we had written it as simply summation of all the immediate rewards. So R1 plus R2 plus R3 plus R4 plus R5. Now what we are doing is we are adding a discount factor here. Gamma, gamma square, gamma raised to 5, etc. So this is called as discounted return or discounted expected return. And this is something which is used in most of the common reinforcement learning formulations. So gamma is a factor which is called as a discount rate. It's like a knob which controls the importance given to immediate rewards and long-term rewards. If gamma is 0, the knob is towards the left. It means that it's only concerned about the current reward. As you turn on the knob from left to right, you start giving more weightage to future rewards as well, or long-term rewards. Now let's look at one small example to illustrate episodic and continuing tasks. So this is called as the cart pole problem. It's a classic problem which is used to demonstrate a lot of reinforcement learning methods or algorithms. Uh, the objective is, let's say you have a cart and you have a pole which is attached to the cart. Now, the question is that, can you move the cart in such a way that the pole does not fall over? The first thing you might say is, why don't you just move the cart ahead? If I just move the cart ahead, the pole will just fall back. Then the next question is, okay, why don't you move the cart back? If I move the cart back, the pole will fall ahead. So the best strategy is to move the pole back and forth, or move the cart back and forth so that the pole does not fall over. We are going to actually solve this problem in some time using reinforcement learning. But right now, we have to write the rewards and returns for this problem by treating it as an episodic and continuing tasks. So first option is treating the problem as an episodic task. The reward is +1 for all the time steps the pole does not fall over, and 0 for all the time steps when the pole does fall over. And this is something which makes sense because let's say the pole falls after 5 time steps, then the reward will be 5. If the pole falls after 10 time steps, the reward will be 10. So this is exactly what we want. We want to maximize the reward, and maximum rewards indicate that the pole will fall after a lot of time steps. So if the reward is 1000, it means that the pole will fall after 1000 time steps, which means that we have managed to control the cart and balance the pole really well. Okay, and then the second option is to treat this problem as a continuous task. So I hope here you've understood the difference between reward and return. Reward was just +1 and 0, but return was this addition of all these rewards which the agent accumulates till the end of the episode. Okay, now here the reward formulation is slightly different because we have a discount factor here. So the reward is -1 for failure. Otherwise, the reward is 0. So let's say the failure occurs after 5 time steps. So what will the reward be? The reward will be minus gamma raised to 5. If the failure occurs after 10 time steps, the reward will be minus gamma raised to 10. Now you will see that minus gamma raised to 10 is actually greater than minus gamma raised to 5. And because of this, this formulation is also correct. So we have two ways of setting up the rewards and returns for the same problem. One way treats the task as an episodic task, and the second method treats this problem as a continuous task. Okay, so according to me, this problem should be always modeled as an episodic task, because for me it's quite intuitive that when the pole falls over, it's obvious that the episode ends and you just have to restart the episode. But in some cases, formulating problems as continuous tasks actually lead to some benefits. Okay, so this is the difference between rewards and returns. Now I come to the main point of this lecture, which is the Markov property. I will confess that when I heard this word for the first time in my college, I was a bit intimidated, and my understanding of Markov property kept on changing. But when I properly learned about this field of reinforcement learning, that's when I really understood the meaning of Markov property. So to understand this property, let's look at some state signals which have some specific property. Imagine that you are having a conversation with someone, right? Let's say you are sitting in a cafe, you are interacting with someone. When we are speaking with someone, the entire history of the past conversation is actually stored in our head. Similarly, when you are playing the game of chess, the current configuration of the chess pieces is enough for you to make your next move. You do not need to keep on referring to, okay, what happened in the first move, what happened in the second move, etc. Similarly, let's say when you fire a cannonball and you ask me the question, what is the next position and velocity of the cannonball? So the current position and velocity is all you need to predict the next position and velocity. The past history does not matter. For example, let's say the cannonball goes like this and the ball is here, and you ask me that, Rajat, what's the next position of this? So there are two ways of giving this answer. The first answer is that you give me this entire trajectory and then I will give you this next position. The second way is that don't give me this entire trajectory. This is enough. Just give me the x coordinate, y coordinate, and the velocity. I will predict the next state. The second approach is what is uh, common between all of these three examples, that the current state is enough to make guesses or predictions. You do not need to rely on the past history. And this is exactly what is called as the Markov property. In all these examples, the state signal, which is the knowledge of people, the current configuration of chess pieces, the current position and velocity of cannonball, they retain all the relevant information from the past. And a state signal that actually succeeds in maintaining all this relevant information is said to be Markov, or it's said to have the Markov property. In most of the RL problems that we are going to look at, we are going to assume the Markov property. Even in some cases, it might be violated, but we are still going to assume this because a lot of algorithms cannot be simplified mathematically unless you have the Markov property. Imagine that you are trying to, solve uh, the projectile motion of maybe a ball, and the mathematics will become so complicated if you consider the entire trajectory to predict the next state. The same thing happens in reinforcement learning. Remember the agent environment interface? We had the agent and we had the environment. And here we only pass. So let's say the agent is in the state ST, and then the action we take, and then we get the next state ST plus 1. Here we are not passing S0, S1, S2, dot, dot, dot. We are only passing the current state to get the next state. So this is at the heart of all the reinforcement learning problems, and it will be an implicit assumption. I won't recurringly tell you that this is because of the Markov assumption, but it will be assumed. As you can see here, to predict the next state ST plus 1, we are only given the current state ST. We are not given S0, S1, S2, S3, etc. So in the most general case, the dynamics depend on everything, all the previous states, but we are going to assume that the dynamics only depend on the current state of the agent. And we are going to take a simple case actually to understand this. Okay, so let's understand this for the card pole example. So my question to all of you would be that I want to basically, let's say this is the card pole, and this is the current configuration of the card pole. It's oriented at an angle theta. So my question to you is that I want all of you to tell me what is the next position of this card pole. Uh, so you might come up with an option, reasoning that, okay, to know the next position, you need to know about uh, the way the wind is blowing. Maybe you need to know about the bearings, what is the friction here. You need to know about the theta. You need to know about the X and Y location of this. So in reality, you need to know a lot of information to predict the next state. But when we solve the card pole problem, we only consider X, Y, theta and theta dot. That's it. And we assume that this state satisfies the Markov property. Whereas in reality, you would need x, y, theta, theta dot. You will need the wind speed. Let's say we call W dot. You will need the bearings, friction in the bearings. You need a lot of different factors. But it turns out that this approximation is actually good enough. So this state signal is approximately Markov. There is no state signal which is truly Markov, but it's always approximately Markov. And another example is the game of draw poker. So this is actually you satisfying the Markov property is extremely difficult, but because to make the next move, you need to know the knowledge of your cards, the bets made by other players, the number of cards drawn by other players, and past history with other players. For example, does Raj like to bluff? Does his expressions reveal something when he is bluffing? But no one really knows about all this unless you're James Bond, I have written here. But most of the poker state signals are non-Markov. People don't think about all these things. Some people just play randomly with gut feeling. So whenever you look at any problem after this lecture, I want you to really understand whether this problem satisfies the Markov property or whether the state signal satisfies the Markov property or it does not satisfy the Markov property. Okay, so now we are going to look at one final thing today, and that's going to be one practical implementation of an RL environment. Uh, in tomorrow's or in next Friday's lecture, we will start looking at different algorithms which are used to solve reinforcement learning problems. But I do not want to make this course overly theoretical, so I want you to basically practice building reinforcement learning agents on your own as I go along. So as I am talking about the practical side of reinforcement learning, our theory will also be revised, and I want all of you to open Visual Studio Code on the side as I'll get along. So that we don't spend much time in that. In case you are not familiar with VS Code, it's a code editor which I use, and I think a lot of people it's quite popular. You can use any other interface to write your code, so that is perfectly fine. Okay, so to implement reinforcement learning algorithms, we are going to use a library which is called as OpenAI Gymnasium. And this Python library was developed by OpenAI. It was called Gym actually back in 2017. But in 2021, the team that developed OpenAI Gym moved the development to Gymnasium. So now it is called as Gymnasium, and it is maintained by Farama Foundation. You will see their name written somewhere on the main website. But now the name has changed from Gym to Gymnasium. I find that Gymnasium is one of the best library to build AI agents or to build RL agents. The main goal of Gymnasium is to provide a rich collection of environments to perform reinforcement learning experiments with a very unified interface. Uh, okay, so now let's understand what actually happens in the Gymnasium library. Okay, so in the Gymnasium library, there are three things. The first is the set of actions which are allowed in the environment. This will be specific to each environment. The second is the shape and the boundaries of the observations allowed in the environment. And the last is a method called step to execute an action. We'll understand all of this much better when we discuss the practical example. But I want you to think about this in such a way that whatever agent environment interface we had looked from a theoretical point of view, Gymnasium allows us to basically implement that framework practically and with a very few lines of code. And finally, a method called reset, which returns the environment to its initial position and obtain the first observation. So Gymnasium has two spaces. One is the action space and second is the environment space. Okay, so and then there are three methods available to create these spaces. There is a box method, discrete method, and tuple method. All of this might be sounding like noise right now, but just stay with me. You'll understand all of it by the end of this lecture. So we will look at a practical example, which is that of a lunar lander environment. This is an environment which is available by default in the OpenAI Gymnasium list of environments. You can actually type lunar lander OpenAI Gymnasium and you will see this page pop up. So in that page, you can see there are two things. The first is action space and the second is observation space. What does the action space mean? Action space means that this is our rover, by the way. What are the possible actions which our rover can take? So let's look at the possible actions. Our rover has 4 actions: 0 for not doing anything, 1 for firing the left orientation engine, 2 for firing the main downward engine, and 3 for firing the right orientation engine. Remember, in the agent environment interface, we have observations and actions. So these are the exact same actions which I talked about. And then that's why the number is 4 over here, because there are 4 actions. And then we have observation space. So what does the observation space mean? You can see that it has, okay, and this discrete is a method, by the way, which is one of the method to create action spaces, as I mentioned here. But the observation space uses a function called box because it's a continuous action space. So box means that, let's say, box low, comma high. This means that, let's say this is 0 and 255. It can take any values between 0 and 255. This is what box means. And this 8 number means there are 8 possible observations. So which are the 8 observations here? These observations are for position, angle, speed, and contact with the surface. So there are 8 possible observations, and for every observation, there is an action being taken. There are 4 possible actions. Now what we'll do is okay, now what are the rewards? The rewards are plus 100 for landing safely, minus 100 for crashing, increased by plus 10 for each leg in contact with the ground, and decreased by 0.03 each time a side engine is firing. So now what we'll do is we will try to actually code it. But before we code, you can see the agent environment interface actually looks like this. The agent is the rover, environment is the entire environment which Gymnasium creates. The states are the 8 observations, actions are doing nothing, going left, going right, or going down. And the rewards are plus 100 for safe landing and minus 100 for crashing. So I'm going to code in front of you right now. So let's see. Let me open up a new workspace, new window. So when you open Visual Studio, you will see something like this. Now here, go to Explorer and click on Open Folder. And you can go to your desktop or downloads and you can create a new folder. You can call it Hands-on RL Bootcamp Visuara. You click on create and then click on open. So you can see this new folder is created. Now go ahead and open up a new file. We are going to call it example1.py. Now before you write the code, you will need one library for this. You can actually do pip install. This you can do in the terminal. I have already installed it. Pip install Gymnasium box 2D. So you can install this library by doing pip install. Okay, I'll talk about that again after some time, but let's focus on the code for now. So firstly, we'll do import gymnasium as gym. Then what we'll do is we will create environment. So environment creation is straightforward. You basically say env equal to gym.make and you just write down the name. So here the name is lunar lander dash v3. Okay. And then what we'll do is we'll sample an action. So you can do sample action equal to env dot action space. So you can see what we are doing here is that we are sampling from the action space which the gymnasium creates in the environment, and we are going to just print it then. Print sample action okay. And then what we are going to do is we are going to sample an observation and to name it sample observation equal to observation space dot sample. Uh, and then we are going to just print this sample observation. Okay, sample observation. And then, yeah, so I think that's it. Let's open up a terminal and then just run this. So you can see that, okay, the first thing I get is sample action is 0 because out of 4 actions it sampled 0, and sample observation is this. You can see there are 8 values. If you again run this, you will see different. So now I sample 1 and I get a different observation. So what's essentially happening is that Gymnasium has created this environment for you. It has created the action space. It has created the observation space. And then you can use these functions to sample from them. Environment action space, environment observation space. Just type yes in the chat if you are able to implement this properly. It's actually around 14 to 15 lines of code, not much. Okay, great. Many of you are there with me. Okay, now we'll actually start to control our agent. So to control the agent, we are going to basically use a function which is called env.step. So I'll just probably show you how this is used. So the first command remains the same, import gymnasium as gym. Then again, we create the environment, env equal to gym.make lunar lander v3. Now here we are going to add render mode also. Render underscore mode equal to human. What this means is that when you render the code, you will see a window open up and you will see the rover moving in that window. But this much is not enough, right? I have just created the environment here. Remember, in the agent environment interface diagram, we need to basically provide the action for each step so that the next observation is revealed to us. Where is all that process happening? And Gymnasium provides a very easy way to set up the agent environment interface. So what you do is basically before you create the step function, you always have to do env.reset. What env.reset does is that it basically resets your episode to the beginning and it gives you your first observation. Okay, so this is a very mandatory step. Don't forget this. Now comes our main function. We are going to do for step in range 200. Here what we are doing is we are going to move the rover for 200 steps. env.render, and then the most important line, env.step, and we are going to pass the action to this step. So this step is going to be env.action space dot sample. So many of, and then finally we are going to just close this off, env.close. That's it. That's our code. Many of you might be wondering what's happening here. What's happening here is that now let's close our mind and try to think what's happening. When we do env.reset, we are collecting the first observation. Okay, so observation is received, but what's the action our agent will take for that observation? That is exactly what we are specifying here. So what the env.step method does is that it takes in an action and it gives you the next state and the reward also. Essentially, this whole step, env.step takes in an action as an input, and as an output, it gives you the next state and the next reward. Now just try running this and see what happens. See here, my rover goes ahead and lands on the surface. It's not a very smooth landing. Can anyone tell me why this landing is not smooth? Why does it behave so randomly and weirdly? You can see it's going anywhere right now. It's basically flipping and doing some weird turns. Let me check the chat. Yeah, Mayank is right. Because we are just passing a random action here. We are not basically learning anything, right? For every observation, we can't pass a random action. Otherwise, this same thing is going to happen. We are not learning anything new in this process. And this is exactly what happens when you just pass in a random action. Now, what we are going to do is we are missing here one of the key elements of the four elements of RL systems, which is the policy. And once we have the policy, it's going to nicely fit here in the step function. And then we can control our rover very nicely. So I want to reach that state, but to understand the policy, we have to cover the different policies, algorithms which are used to solve reinforcement learning problems. And that is going to be the focus of our next lecture. We are going to look at the three horsemen of classical reinforcement learning, which are dynamic programming, temporal difference methods, and Monte Carlo methods. And then we'll slowly proceed to deep reinforcement learning. Let's see if there are any questions. Yes, so this is a pre-built environment in OpenAI Gymnasium, but the best part is that you can create a custom environment also, and you can run uh, your agents in those custom environments. So it's a very nice framework for creating your own RL environments, developing policies, and running them. There is another framework which is used for creating policies, which is called as Stable Baselines 3. That's an amazing framework, but I'm going to talk about it in lecture number 3. So that's when we'll be integrating OpenAI Gymnasium with Stable Baselines 3, and we are going to combine the agent environment interface with the right policy and see how beautifully it works. Okay, so now for the pro people, all the notes will be uploaded on the dashboard, and I'll be uploading key resources and the code files also. Uh, the video lectures will be shared with everyone, but pro people will receive all the resources which I have used to learn in this process. So it will really help them in their learning journey. As I'm moving along, and I encourage all pro people to join the Discord group also, because we'll be discussing about interesting things related to reinforcement learning there. Uh, so as we move ahead, I want to emphasize on the fact that for a longest time, RL has been considered as a very theoretical and complex field. But as we go through these lecture series, I want to help you develop confidence of implementing RL algorithms. You can, even now, you can sit down and implement PPO, but you won't understand the logic behind it, how it works, how it has evolved through the years. And understanding the development over the years is what gives us the right amount of confidence before we actually implement practical projects or research in this field. As I said before, we are going to enter the era of experience soon, transitioning from the era of human data. So we are now saturated with data. There is only so much data you can pre-train the LLM on. The next stage is where the model learns by collecting its own experiences. So I'm going to post all the resources in the dashboard and Discord for the pro people after this lecture is over, and I'll see you in the next lecture. And it's going to be a very interesting lecture. It's going to be about understanding the three horsemen of classical reinforcement learning. So that will be very interesting, and we'll have a practical session towards the end of that as well. I won't prefer Google Colab for these courses. I myself have run it in VS Code, and I tried in Google Colab, but there were some package issues I faced. So VS Code is the best for most of the sessions. Okay, everyone. So it was great interacting with all of you, and I look forward to seeing you in the next lecture, which will be next Friday. It will be the same link. Thank you, everyone. Bye.